So we would like to discuss a very important subroutine that is used in many quantum computing algorithms, and that is called the quantum Fourier transform. The quantum Fourier transform, in tandem with the Grover search algorithm or subroutine, forms the basis of many problem solving tasks in quantum information processing. So it's really important that we understand Grover search and the idea of quantum Fourier transform really well. For example, the quantum Fourier transform helps us to estimate phases. It helps us to find out the eigenvalues of Hermitian operators, eigenvalues of unitary operators. It helps us determine the prime factors of a large number, and this is one of the most crowning achievements of quantum computing, which actually gave a boost to the whole discipline of quantum information processing and which brought quantum computing from the textbook to the real market. So it's at the heart of the quantum revolution in one sense. So in order to discuss the quantum Fourier transform, I'm sure you've already seen the idea of a normal Fourier transform. So if I have a signal, some signal, and this lives in some space, for example, it lives in the time domain, then of course this signal has a particular expression. And if it's periodic, then it means it also has a certain frequency content. Aperiodic signals also have frequency content. So the Fourier transform takes a signal living in one domain and transforms the signal or represents the signal in some other domain. For example, you could move from the time domain to the frequency domain. And if this were, say, a sinusoidal signal with a certain frequency omega naught, then in the frequency domain, the signal could be represented by a peak at omega naught. And since we talked about complex signals, a peak at minus omega naught. So whatever the signal in the time domain looks like, it can be transformed through an integral transformation into another domain. And the idea of the Fourier transform lets you go from one domain, say the time domain, to the frequency domain. The inverse Fourier transform lets you go back. So you could have time and frequency, you could have position and momentum, also called the k-space, and so on. And all of these concepts are really important in physics. For example, when you learn about condensed matter systems, you look at the Brillouin space. The Brillouin space is electronic wave function in the k-space or the momentum space. Sometimes it's easier to deal with signals in the Fourier domain, in the frequency domain, than in the time domain. However, when we talk about information processing and we talk about computing, these continuous Fourier transforms are replaced by their discrete versions. So we have this idea of a discrete Fourier transform. So a discrete Fourier transform will take this signal, sample it at precise points in time. That's what a digital computer does. It cannot deal with continuous signals unless you have an analog computer, and then you put it into a digital domain. And there's a certain formula to compute the discrete Fourier transform. Suppose I'm given the vector x, right? So I represent this vector by thick boldface x, and this x has certain components, for example, x1, x2, x3, and so on up till x, say capital M. So this is a vector living in an n-dimensional Euclidean space. Now, if I were to find out the Fourier transform, the discrete Fourier transform of this x, let's say that that is represented by y. So y is the discrete Fourier transform of x. Sometimes it's given the same symbol and you put a tilde on top of it. Remember that this x in shorthand is some coefficient xj. where j goes from 1 to n. So this is my initial vector. Now, if I were to take the discrete Fourier transform of this vector, I will form another vector, y. So I'm starting from one vector, I'm going to another vector through a process of transformation. So if I represent my digital Fourier transform by a box, DFE, it takes in a vector x and outputs a vector y, which is the Fourier transform of x. And if this x has n entries, it has a length n, this y will also have a length n. And the definition of the discrete Fourier transform goes as following. Y equals, now y will have certain components, so this y will comprise of yks, correct? y1, y2, y3 and up to yn. So k also goes from 1 to n. Now the kth component of y, which is also called a Fourier coefficient. So now x has been represented in the Fourier space. A new vector has come up, that is the Fourier transform of x, and the components of y are called the Fourier coefficients. These Fourier coefficients are given by definition xj e raised to I 2 pi jk n, where where j goes from 0 to n minus 1. So I can start labeling these from, so these could be, let's call this capital N minus 1, and let's start from 0. Let's call this capital N minus 1. So this is the definition of the Fourier transform of a vector. And then you take all the xj's, multiply each xj with this exponential coefficient. J and k are your running variables. So you take a sum over all j's and you'll end up with one component of the Fourier transform. So this is our definition of the discrete Fourier transform. And of course you also need to normalize this, so you put square root n here as well. So by the way, different authors use different conventions. Some put this square root n here, some put it in the inverse transform, and so on, but some put a minus sign here. Let's stick with one convention. Just to give you an example, so let's talk about an example in the quantum domain. So this is our Fourier transform. Now likewise, in the quantum domain, we can talk about a quantum Fourier transform. And what the quantum Fourier transform does, it takes a ket x, which might be given by xj ket j sum over all j's, j goes to from 0 to n minus 1. This is a possible expansion or representation of a vector x in a certain basis state. Alright. Now if I were to take the Fourier transform of this x, so let's represent the action of Fourier transformation by a unitary operator uq. So when uq acts on a quantum state x, I get another quantum state ket y, and its coefficients are given by yk ket k where yk is the discrete Fourier transform of the vector that is made from the coefficients of this vector. So this is our definition of the quantum Fourier transform. Now what does this mean? Let me recap. I have a quantum state, a pure quantum state, ket x. I've expanded this in a particular basis. The basis vectors are the ket j's. So the ket j to be ket 0, ket 1, ket 2, ket 3, all the way up to ket n minus 1. And if this is a legitimate basis for this Hilbert space, each one of these basis vectors will come with a coefficient, a complex number, xj. So this is how this initial state is composed. I'm just representing this initial state in a particular basis. Now if I were to take the Fourier transform of this state, I will get a new quantum state, ket y. Now the ket y will also be represented in the same basis because we're not moving out of the Hilbert space, we're remaining inside the Hilbert space. But this time the probability amplitudes for each basis state are given by their Fourier coefficients corresponding to the probability amplitudes of the initial state. So this is our conventional definition of the discrete Fourier transform. So I look at my initial states, I make the probability amplitudes into a vector and I take the discrete Fourier transform. Now what results are the Fourier coefficients. I pluck those Fourier coefficients and put them into this thing. So this comes here. This is the definition of the quantum Fourier transform. Let me give you an example. Suppose I just have one qubit, right? Just one qubit to make our life simpler. So my n, small n is 1, my capital N, which is 2 raised power n, is 2. One qubit, two basis states. And I also suppose that my initial vector, ket x, is simply ket 0. Right. Now this means that my x naught is 1 and my x1 is 0. So just look here, my ket x can be expanded and the probability amplitudes are x naught is 1 and x1 is 0. Got it? Now let's find out the discrete Fourier transform of this vector. This is a vector of numbers 1, 0. Let's find the discrete Fourier transform of this x. So of course, the size and dimensionality of the problems is changing. So I have a y0 and a y1. y0 will be equal to, so I'm just going to expand this thing over here. I have two states. So 1 over under root 2. x0 is 1. e I 2 pi. Now my j is, for this is 0. 0 times 0 over 2 plus my other x is 0, so whatever comes with this doesn't really matter. So this thing becomes 1, so my y0 is 1 over under 2. Let's compute y1. y1 likewise is 1 over under 2, my x0 is 1, e I 2 pi, j is 0 dotted 1 over 2 plus my x, this is 0 anyway. This is again 1 over under 2. So the Fourier transform of my initial state, let's call this 0 tilde. So now my initial quantum state ket 0 is written in the Fourier space. It's a new quantum state and that quantum state is 1 over under 2 ket 0 plus 1 over under 2 ket 1. So I started off with this state here, and then I took the Fourier transform of this state, the quantum Fourier transform, I ended up with this equal superposition. So the Hadamard gate for a single qubit is implementing a quantum Fourier transform operation. For a single qubit, that's what a Hadamard. In fact, you could take arbitrary states, x0 could be some x0, this could be some x1, anything. And you'll find out that the Hadamard gate does the job for a single qubit. The Hadamard gate is a quantum Fourier transformer for a single qubit. Alright?
Yes.
Now you can extend this to higher dimensions. So this is just a simple example. In fact, a general scheme is going to emerge later. Now if you look at the block sphere, this quantum state that we started off with is on the north pole. And when you take the Fourier transform of this quantum state, so this is ket 0. And when you take the Fourier transform of this state and represent the new state, you can do it representation on the block sphere because it's single qubit, then I get this state that lies in the equatorial plane. So this is ket 0 with a tilde sign on it. So what a Fourier transform is generally doing is that it is taking a computational state ket 0 and adding getting phases out of it. So here the phase is 0, but if you were to do this for higher dimensions, you will get some phase on the equatorial plane. So it's creating phases. So that's what generally quantum Fourier transform does. If you look at this formula here for a discrete Fourier transform, these are phases that are being added to the coefficients. The phases are being multiplied to the coefficients and then you take the sum. So this is like a flowering action. So a state comes in, it spreads out, and each spreading out, each component that is spread out picks up a phase. Now this phase becomes really important when you want to do certain quantum algorithms, because everything lies in the phase, as you might have imagined by now. Now, all right. So let's look at a general form for this unitary operator. And by the way, we would like to see why is this a unitary operator. We just like to confirm that this is a unitary operator. All right. Any questions up to this point? You had a question?
No, sir, clear.
All right. So now let's look a closer look at UQ. First of all, a general form for UQ. So one convention that is generally used, it's a notation. This term E I 2 pi j k over m is also written as omega raised by jk. Okay, so this is a notation for convenience. Soon you will realize that these omegas have something to do with the roots of unity. Anyway, now if I were to propose that my UQ is given by the following, is given by 1 over under root n First of all, U must be an operator, correct? Because U is taking a ket and transforming it into another ket. So it must be an operator. And what should the size of this operator be? How big should this operator be?
As big as the vector.
So how big is the vector? How many entries does it have?
For us,
So suppose there are capital N entries or small n. So can you tell me how much should this vector be? How big is this vector? Is it, how big is it? Capital N, right? So this must be an n by n matrix. It must have n square dimensions, right? So each one of these j, k goes from 0 to n minus 1. Alright? So let's check whether this is indeed giving this desired operation. So if I have UQ and this acts on some state, say ket m, or better still, let it operate on some arbitrary state, get x. Let's see what happens. G, you have a question?
Sir, why the sum goes to n minus 1 and not?
Because you're starting from 0. You start from 1, this can go up to capital N. So the convention is just to be consistent with authors, I'm starting from 0 up to n minus 1. So suppose this operator acts on some quantum state ket x. That ket x is given by this thing, the general form of a quantum state. So 1 over under root n j k omega is for j k ket bra j. So this is an outer product, and this acts on x. So x. So let me use the index L now. So I'm using L because I want to differentiate this from K and J. So now I just 1 over under root n jk omega jk ket j bra j ket L, and of course an XL here as well. And I need to sum over L as well. But this is a Dirac delta function which is non-zero only when L equals J. So I can remove the sum over L and replace this XL with an XJ. So I get omega jk xj ket k. This is j 1 over under root n correct? But this is, you already noticed that this is simply yk. This is the discrete Fourier transform of all the x's. This is, which is indeed the Fourier transform of x. Hence, this is the legitimate quantum Fourier transform operator. Got it? I think you're losing out here. Does this work? I give you 2 or 3 minutes to just ponder over this, assimilate this, and see if it's making sense. So what I did, I propose an operator. Every operator can be written as a sum of outer products. So this is the outer product. And this is the coefficient. Now I take this operator and apply this on an arbitrary input state. Do the algebra here, and this turns out to be equal to the coefficients that this state picks up are the same as the discrete Fourier coefficients of the initial vector. G. I did that because this thing here is the Dirac delta function or the Kronecker delta. This is non-zero only when L equals J. So I don't have to pick up all the L's. I just pick up that L which is equal to J, and I'm already doing a sum over J. So I just replace this XL with an XJ. That's what I've done. Sorry, this K? वो तो बाहर हो गया. I'll give you 2-3 minutes to assimilate this. We really need to understand how this is working, because this is going to appear everywhere in the quantum algorithms. All right, should I move on? So the next question I would like to ask is the following. unitary. Now, how do I prove that UQ is unitary? Because if this UQ is unitary, I can implement this on a quantum hardware, on a quantum computer, because a quantum computer works on reversible states. It works on unitary operations. So for that, the quantum Fourier transform has to be unitary. So I need to figure out whether this is unitary or not. So how do I figure that out? How do I know that this is unitary? If I take the right, so a unitary operator is one whose adjoint is equal to its inverse. So I need to multiply one method of doing this is finding the inverse and seeing whether it's the adjoint of the original, or I could take the matrix and multiply it with its adjoint and see if I get the identity matrix. So let me take that approach. So this is my UQ. Let's find out the adjoint of this. So the adjoint of this is, let's do this carefully, 1 over under root n, again sum over j of nk. Now omega is this thing here. So this is a scalar. I need to find the complex conjugate of this. So this will become e minus I 2 pi jk over n. Now what's the adjoint of this outer product? It's going to, you just invert the bra and the ket. So this is going to be ket j bra k, right? So this is the adjoint of this operator. Now I want to see whether the two are mutually inverses. Alright? So now how I do, I just multiply the two and see if I get the identity as my final result. So I take my UQ dagger, I take my UQ and lay them out together, concatenate them together with one another. So I'm left with 1 over n jk e minus I 2 pi jk over n ket j bra k, and for UQ I write the original thing 1 over under root n. I've already pulled it out, put 1 over n in its place. Instead of jk I now use L and m. E I 2 pi L m over n ket n bra L. Right? Correct? Fine. So now just expand, so I have a big summation. 1 over n 1 over n j k l m e minus I 2 pi over n j k minus l m ket j bra k ket m bra l. Now this is the Kronecker delta, right? M must equal k, otherwise everything just vanishes. So I can drop the summation over m, j, keep just l, e minus I 2 pi over n, jk minus lk, right? Right? And 1 over n. So this becomes, I could take minus I 2 pi over n j minus L k ket j bra L 1 over n j k here. Okay. Fine, I just done some remanipulation, shifting of things to the left and right. Now look at this thing here. This is an integral. Now j, by the way, is an integer, L is an integer, and so is k. All of this is an integer. And there's an identity that is really common in when you talk about complex numbers. And the identity goes as the following. So k e minus I 2 pi some integer p k. So if I take this sum, to be exact, this is what it is. This is this sum, right? If this sum is, if p is 0, if p is 0, then each one of these terms is 1. And I'm taking n of these terms. So my answer will be capital N. Right? So I'm taking, so if this p is 0, so my running variable is k. So k is going from 0, 1, 2, 3 all the way up to capital N minus 1. So my running variable is k. But this p is an integer that I can choose. If this p were 1, if this p was 0, then this exponent will be e raised to the power 0, which is 1. And I'm taking n of these terms. So my answer will be n, capital N. If this p, which is an integer, is anything but 1, say anything but 0, say 1, 2, 3, 4, minus 1, minus 2, anything but 0, besides 0, then this term is going to vanish. The sum of all of these terms is going to be 0. And the reason is that these will be roots of unity. So this term is n only when p equals 0 and it's 0 elsewhere. Now what you could do as a check, suppose my capital N is 2. Choose any other value of p besides 0. You will find out that these numbers are phasors that lie on a circle. So example, so this is a very popular identity. It's used quite a bit in complex analysis, very commonly used in quantum field theory and so on, and when you talk about second quantization, it's really popular. So for example, suppose my capital N is 2. Let me just give an example. And my P is 1, right? Non-zero. Let's see what this thing turns out to be. E minus I 2 pi, P is 1, K is 0, N is 2, plus E minus I 2 pi, P is 1, K is 1, N is 2. Now this is 1. What is this? This is minus 1. This is 0. And what is this number? This number really is, if I were to draw a circle, it's called an organoid diagram. This is my origin. This number here is e raised to the power 0. This is represented by an arrow which is pointing in this direction. This is my real axis and this is my imaginary axis. So this is an organoid diagram in which I would like to plot these complex numbers which are called phasors. This number is e minus I pi. So its phase is pi. This number would lie here. So when I take the vector sum of these phasors, I will get 0. if my n is something else, if my p or my p is something else besides 0, I will just take all of my phases and will point in direction so that their vector sum is going to add to 0. These are called the nth roots of unity. So these numbers are the nth roots of unity. And you take the sum of the nth roots of unity, all of them, you will get 0. Alright? So what are the cube roots of 1?
1 omega omega square.
Right. So they point at 0 degree, 120 degrees, and I think 240 degrees. So it makes a triad of vectors. You add them up and get 0. So this is the identity you need to remember. Now with the help of this identity, this thing, what does this thing equal to? This thing turns out to be non-zero only when j equals L. Right? When this thing is equal to 0, which means j must equal L. And in that case, it takes up a number capital N. That N cancels off with this. So I'm left with what is this thing? What is this outer product equal to? If this is just equal to the identity. So I've shown that the operator that I've written, the U, Q, is indeed unitary. If I were to do this for completely, I would just also do a calculation in which I invert the order of these operators. So since U is unitary, I must have a circuital implementation of this. I must have a quantum circuit that implements the Fourier transform. Because the quantum circuit is made up of reversible unitary gates. NOT gates, swap gates, control rotations, control NOT gates, control phase gates, poly gates, etc. All of them are unitary. They are rotations in the Hilbert space. So now, once we have the hang of the quantum Fourier transform, we would like to see what it really does and what's the meaning, the intuition behind the quantum Fourier transform and what kind of circuit is required to build this up. So let me, before I move on to the circuit, any questions? Let's look at a 3-qubit state. And let's look at the state 0, 1, 0, right? A Zeeman state or a computational state. And let's find out the quantum Fourier transform of this state. And let's use our conventional definition of the discrete Fourier transform. So I give you 5 minutes to work out what the quantum Fourier transform of this state is going to look like. What is this state going to look like? Just take your time and work this out. So use your definitions over here and see where you get. So remember, in this particular case, so this is the decimal number 2. 0, 1, 0 is the decimal number 2. So my x naught, x2 is 1, all the other x's are 0. So I want to find out my y naught, my y1, my y2, my y3, my y4, y8. Let's simplify this problem. Let's look at a 2-qubit state. So I need to find out y0, y1, y2, y3. So my y0, so my small n is 2, capital N is 4, so 1 over 2, my x naught is 0, x1 is 0, x2 is 1. So my j is 2 here. So e I 2 pi j is 1, my k is 0 over capital N is 4. Right? So my capital N is 4. This turns out to be e raised to power 0 is 1 half. This is my y naught. My y1 is going to be, I only need to take x2, the x2 term, because all other x's are 0. 1 e I 2 pi j is 1, now k is 1. This is e I pi over 2. This turns out to be iota. This is e I pi over 2. This is iota over 2. My y2 is 1 half 1 e I 2 pi, my j is 1. Now my k is 2 over 4. I'm just using this formula, by the way, nothing fancy here. I'm just using this formula. That's it. Just plugging it in. Right, so I'm finding out the quantum Fourier transform through the discrete Fourier transform of the probability amplitudes. So this is going to be E I pi. This is E I pi is -1. Correct? My y3 is going to be equal to 1 half 1 e I 2 pi, my j is 1, my k is 3. This is going to be 1 half e I 3 pi by 2. This is cosine of 270 degrees, 0 plus iota sine of 270 minus iota. Therefore, the Fourier transform of this state, if I were to use a symbol 1 0 with a tilde sign on it, is going to be 1 half. Now y naught is the coefficient of the state 0 0. This is the coefficient of the state 0 1. This is the coefficient of the state 1 0, and this is the coefficient of the state 1 1. Correct? Now this is a separable state, by the way. I'm just going to look at what this state looks like. Luckily this is a separable state. It's a separable state because I started off with a very simple eigenstate or a very simple computational state 1 0. So I can express this as 0 1 1 over minus So the first qubit is in a superposition, and so is the second qubit in a superposition. And if I were to draw this on a block sphere, so tiny block spheres, first qubit, second qubit. Luckily, I can draw two block spheres because the state is separable. Normally, I wouldn't be able to do that. Let me finish. So the first qubit is has acquired a phase 0, -1, so it's at the back here. And the second qubit has also acquired a phase, it's I think here. So starting off with a computational state, when I took the quantum Fourier transform, I have given phases to the two qubits. And these phases are, this is 180 degrees phase, this is a 90 degrees phase, the azimuthal phase. So this is the mechanics of doing a quantum Fourier transform. I start off with some state, I take the Fourier transform, I have put in phases into the quantum states. G.
How are you assigning states with the coefficients? Say 0, 0 ka coefficient 1 or
because this is the order that I'm working with. So if you, that's embedded in here. This is what the kth state. The kth state will have k at the top. So if I were to take y0, I will put 0 instead of this k. So that I know that the answer that I am getting, I take a sum over all the j's and keep this fixed. I will get a fixed by k. That's what I've done over there.
that just tells us about 1.
That just tells us of, so this is my overall state. My overall state is y0 ket 0. So I'm going to expand this, right? Plus y1 ket 1 plus y2 ket 2 plus y3 ket 3 and so on. Y n minus 1. So this is what my state is. So I'm finding out each of these coefficients one by one.
सर वो x2 is equal to 1 किस तरह लिया सर आपने?
Sorry?
x2 is equal to 1 जो लिया.
Because initially my state is my 1 0 can also be written as xj, right? So this is some x naught right? So only this term is non-zero. So what I've done is generally you represent these states by label zeros and ones, but you can also convert them to decimal. That's what, when we take the sum here, 2, 3, 4 are the decimal representations of the binary digit sequence that is being formed by those states, right? So is this clear? So this is one example of a quantum Fourier transform. By the way, how many computations are needed? So for each k you need n multiplications. So you need sum. How many terms do we have in the sum? M, capital M. Right? So this is n sums. And how many k's do you have? N. So you need of the order of n square operations. N is, by the way, 2 raised power n. So you would really need n square operations. Or now n is 2 raised power n, so you need 2 raised power 2n operations. If you increase the number of qubits, the complexity of the problem goes exponentially. So the classical Fourier transform takes exponential amount of resources, time, number of bits, number of computations that are needed. And there are efficient algorithms that can replace this Fourier transform even in the classical domain, and one of them is FFT, fast Fourier transform. That does the task in log n times, but I don't want to go into that detail. Quantum Fourier transform brings this problem to the realm of polynomial time scales. Anyway, any questions up to this point about the quantum Fourier transform? The gist is that you start off with some state and the quantum Fourier transform creates a distribution of phases, carefully selected, curated phases. The inverse quantum Fourier transform will do the inverse thing. It will take all the phases and put it back onto a computational basis, onto a computational axis. Alright, so now I want to do something slightly more complicated. I would need access to my notes here. This done on slides is easier, but before I move on, so what I would like to do now is, what does the quantum circuit look like that implements the quantum Fourier transform, that then becomes an ingredient for other quantum algorithms? I need to implement this on a quantum computer. But before that, I would like to also mention the matrix form. If you look at the matrix form at the top of the middle blackboard, UQ, thing that I put in a box, can you attempt to put this in matrix form? As a matrix. Represent this as a matrix in the KJ basis. And when you do implementation as part of your homework, when you actually deal with matrices, this will come out really handy. So each element so I have a 1 over under root n. Now there are rows in this matrix and there are columns in this matrix. The ket k over there at the top, let me rewrite this over here. UQ is 1 over under root n, sum over j's, sum over k's, omega jk, ket k, bra j. So you need to understand how to write an out of product in matrix form. Now this k is a variable that goes from 0 to n minus 1. J is also a variable that goes from 0 to n minus 1. Alright. So the rows are represented by the k's. Let me just, so the k's represent the rows and k goes from 0, 1, 2, 3 all the way up to n minus 1. This is not, these labels are not a part of the matrix, these are just identifiers. So this is the 0th row, the 1st row, the 2nd row, the 3rd row, the n minus 1th row. Columns are represented by these outer products, j's. This is, I'm just telling you about a mnemonic, something, an easy way to remember how to write the matrix from an outer product form. This is a mnemonic, yaad rakhne ka tarika hai. Now the j's represent the columns, so 0, 1, 2, 3, all the way up to n minus 1. So what is the entry here? This is the entry here. So if I just have one here, just one here and everything else is 0, that would correspond to this outer product. This outer product, if I want to write this in matrix form, this will have a 1 here and 0 elsewhere. This thing will be the 0th row, first column. This will have a 1 here and 0 elsewhere. Alright? 3, 4 will be in the this row, actually the 4th row, 0, 1, 2, 3, the row with the index J3 and column index 4, 0, 1, 2, 3, 4 here. So if I just write this outer product, this means I put a 1 here and 0 elsewhere. Now if I just use this scheme over here, now I am representing the entries of this matrix by yellow. The white is not an entry in the matrix, these are just placeholders. So I can 1, 1, 1, 1, because anything raised to 0 is just 1. Likewise, this is the first column, all ones. This thing here is omega raised to power 1 into 1 is 1. This is omega squared, omega cubed, omega raised to power n minus 1. These coefficients here. this thing will be omega square, omega raised to power 4, omega raised to power 6, omega raised to power 2 into n minus 1. Likewise, this goes down, this goes down. Let me write down the last row, perhaps. Omega n minus 1, omega 2n minus 1, and so on. This will be omega n minus 1, n minus 1. This is what this matrix looks like. And each omega is a phase of amplitude 1 e raised to power I. For example, this thing here, I expand this as ei 2 pi n minus 1 n minus 1 over n. This is this number here. So each one of this is ei 2 pi and some integer, or not necessarily integer, sorry, some rational number here, okay? So this is how you construct this matrix. And by the way, this is also and you can tell by looking at the matrix that this is unitary. Anyway, so let's move on. Let's look at the circuital implementation of the quantum Fourier transform. It's going to be unitary. You take it. It's not Hermitian. It's unitary. You take the adjoint of that matrix, and then find the inverse. It will be equal. Why? Because if I take any element, say omega square, the complex conjugate of this is going to be 1 over omega square. And then this will come into this position. Then you multiply off with the original, you get identity. So the circuital implementation. Now for the circuital implementation of the quantum Fourier transform, for that we need to clarify a few notational points. Suppose I have a state ket j, ket 1, ket 2, ket 3, ket 4, anything. Now I can, I have n qubits. Right. So really this state is a shorthand decimal notation of J1, J2, J3 up to Jn, where each J with alpha, which could be 1, which could be anything, say some number up from 1 to n, could be 0 or 1, correct? So I'm just using this notation here. So this ket j can be represented in binary form like this. It could be represented in decimal form like this. Correct? ये समझ आ गई बात? For example, suppose I have 4 qubits. With 4 qubits, ket 15 is this thing. Ket 14 and so on. So I can take a binary representation and put this in decimal form. By the way, when you talk about computing and information processing, you also have to be cognizant of the sequence. Generally, this thing is called the most significant bit, and this is called the least significant bit. By the way, if I were to take these j's, how can I express the decimal number j in terms of the j1, j2, j3 and so on?
Sir, please repeat the question.
So I have these j1, j2, j3. I want to express this decimal number j in terms of these things. सिग्मा साइन, लेकिन वो क्या बीच में क्या आएगा? यहाँ पे 1 और 0s हैं. I would like to convert this into decimal. So any sequence of bits that I take this sequence of bits. This is J1, J2, J3, J4. From J1, J2, J3, J4, I want to find J. There has to be a formula for this. What is that formula?
Sir,
Yes?
Say 2 to the power of that bit multiplied by the even corner.
Aha. So I take J, say L, 2 raised to power n minus L where L goes from 1 to n. Is this correct? I think it's correct. So the most significant bit is J1. So most significant J1, 2 raised to power n minus 1. So if I expand this, J equals J1 to n minus 1, J plus J2 to n minus 2 plus J3 to n minus 3 all the way up to Jn 2 raised to power 0, which is 1. Does it work over here? It works. So this is my prescription for J. Alright, this is a notation. So I'm converting between decimal and binary. Is this clear? Okay. Another notation, so this is just a new notation that is common in this literature, is the following. So if I have 0 dotted with Jn plus 1 so 0 dot jm plus 1 up to jm plus, but each one of these could be 0 or 1. So this is a fractional binary number. This is really equal to jm 2 raised to power minus 1 plus jm plus 1 2 raised to power minus m minus 1 2 raised to power minus 2 plus j m plus r 2 raised to power. Now how many? So we have r plus 1 in this way. So this is what this fractional binary number looks like. So here there are r plus 1 entries, right, in my notation over here. So this, the first digit right after this decimal, this binary decimal picks up a phase 2 to the power minus 1. This picks up the next 2 to the power minus 2, so you divide by 4, then you divide by 8, and you go all the way. So the m plus rth thing is picks up, so the exponent is 1 bigger than this thing, so that's why I with a minus sign. So instead of r, I have r minus 1 with a negative sign. Alright, so this is my second piece of notation. This of course can be represented as sum of j t 2 raised to power minus so this number here is t, where t goes from m to this is right. So I can just work this out. Anyway, if you want, you can work this out. This is going to take some kind of thinking of what these indices should be. Do you understand this point? Up to here? So this is j t, where t goes from m to m plus r, and this factor here is this is j m plus k 2 raised to power plus 1, right? I think this is it. Anyway, so this is my second piece of notation. So now what I would like to do, what happens when the Fourier transform acts on the state ket j? My idea is that I would like to implement this in circuit form. So I want to find out what happens when uq acts on j. Alright, so let's start off with our definition for uq. Our uq is 1 over under root n sum of omega. Let's choose mk. Instead of j, I use mk. Sum of over m and k, ket k bra m. This is acting on j, and j really is this thing. Let's put this j in this step here. Now this is a single quantum state. It's not a superposition, it's a decimal state, say 001, etc. Now what happens when the Fourier transform acts on this state? Right? So I can just notice that if I were to take the inner product of ket m with ket j, the m's are going to vanish unless the m equals j. So I'm left off with 1 over under root n correct? Now let's expand this a bit further.
सर ये पर सब खत्म हो जाएगा.
सॉरी हाँ बिल्कुल J पे सम खत्म हो जाएगा. Sorry, J पे सम खत्म हो. Now the next step is U Q acting on J equals 1 over under root n sum over k omega j k cat k. Now this cat k is really also just like the j. This can also be expanded as k1, k2, k3 all the way up to kn. And you can replace this summation k with sum of k1, k2 all the way up to kn, where each one of them is 0 and 1. Can't you do that? You can do that, right? So now we replace this decimal representation by the binary representation as a sequence of n binary digits, n bits, k1, k2, k3 all the way up to kn. And each one of these, so now instead of having one big variable k, I have n small variables and each variable is a bit, 0, 1. Right? And 1 over under root n is going to live with us forever. This omega jk is e I 2 pi j. Now this k over here can also be expanded, just as we've expanded this j. This k can also be expanded. So this k, when expanded, let's call this variable L. KL goes from 1 to n. KL 2 raised to power n minus L, and of course there is a 2 raised to power n as well here, capital N. Oh, this might look a bit cluttered, so right? Now, if you look at this 2 raised to power n can be cancelled off with this 2 raised to power n. So I'm left off with 1 over under root n, k1, k2, kn, 0, 1, e I 2 pi j. Now here what do we have? We have KL and 2 raised to the minus L. So 2 minus L. And we have K1 plus K2 plus K3 plus K4 all the way up to Kn. But now you have an exponent. So if you have an exponent A plus B, you have a sum in the power of the exponent. You can convert this into the product of two exponents, can't you? So now you have all the possible k's in here. Yes, please.
What about the k and exponent? J
Here,
exponent with 2 pi j.
so this k is replaced by its expansion. Just as I can expand j in terms of these binary digits, I can also expand k in terms of its binary digits. So instead of k, I've written this thing. Right? So now what we have is, if I were to take the sum of all the k's, k1 plus k2 plus k3 all the way up to kn, right? I could also write this as a product of KL. This product goes here. L is 1 to n, and this KL is either 0 or 1. This is slightly messy, right? Just a minute. बिल्कुल ठीक है, बिल्कुल ठीक है. So what have I done here? I started off with this thing, then I expressed my k as a binary sequence, k1, k2, k3 up to kn. Each kl is 0 or 1. And then I expanded this k in terms of the binary numbers of the kls. Each one of them is 0 or 1. Remember, each kl can have only two possibilities, 0 or 1. That's it. K1 can be 0 or 1, K2 can be 0 or 1, K3 can be 0 or 1 up to Kn. Each one of them is a binary digit. Now I express this decimal k as the sum of binary digits. Now since this is an exponent, and in the exponent we have a sum, that exponent of sums can be written as a product of two exponents. So now we have a sum of n terms, small n terms. I've written this as a product of n terms. Got it? Now, if I were to expand this, so if you just want to make sense of this, this is 1 over under root n. I'm just going to expand this a little bit so that you understand what's going on. Each one of these k's could be 0 or 1, and I have my first k sub 1, right? So I could e I 2 pi j 2 raised to power, my L is 1, k sub 1. Now this thing is, and I multiply this with e I 2 pi j 2 raised to power minus 2 k sub 2. Remember, this is now just a number. It's a scalar, amplitude 1, just a phase. This is just another phase. And this goes all the way up to ei 2 pi j 2 raised to power minus n kn. But all of this is acting on k1. So now I'm just going to write this in a different fashion. I'm going to write this as a tensor product on all the n qubits, k1, k2, k3, kn, right? I can do that, can't I? I always do that. Now when this happens, so armed with this concept, I could write this in the following form: 1 over under root n. Each one of your k's could be 0 or 1. I can write this as e I 2 pi j 2 raised to power minus l kl acting on its specific kl. And then I can bring this out. Bring this out. Put the summation sign back in. You can write this as 1 over under root n n1 to n. Now this kl can be 0 or 1. So when this is 0, this thing becomes 0. So I get cat 0. Because this becomes e to the power 0. This is 1. 1 cat 0 plus e I 2 pi j 2 raised to the power minus l cat 1. So this is what happens when a quantum Fourier transform acts on ket j. And if I were to expand this for ease of understanding, This is just a tensor product of n qubits. For ease of understanding, let me write this out. 1 over root n. First qubit get 0 plus ei 2 pi j 2 to the power minus 1 get 1. This is my first qubit. Second qubit, what happens to the second qubit? Plus ei 2 pi j get 1. Second qubit. Third qubit. And so on. All the way up to my nth qubit, the last qubit, just a minute. I can simplify this further. I'll tell that about that in the next lecture. Yes, please.
Sir, when you can we like continue this in the next lecture? Kafi time.
Right. So do you get this? At least this much. So please go home, go through your notes again. I've done this really systematically. Maybe with slides it would be easier for me, but at least I think this will give you the whole idea of how this is unfolding and unpacking. Now in the next lecture, we'll put this in the notation that I've described over there and see what kind of circuits or what kind of gates are needed to implement this. Thank you very much.